In this video, we're going to finish off Chapter 8, and to do that, we're going to talk about how to find sample sizes. Now, basically, the idea is we've been dealing with confidence intervals, and we've seen that there are some intervals that have a bigger margin of error than others. In other words, we have our point estimate, and we have to build in some error on either side. And so we have some that maybe when we go out and do our sample, we take a certain sample and the margin of error, I don't know, if we're taking a sample of height, maybe our margin of error is like 4 inches. So we took our point estimate and we have 4-inch margin of error on either side. Now that 4 inches might be too far spread out than what's actually useful in a practical sense. And so what we're going to do is we're going to say, well, how big of a sample do I need so that my height has a margin of error less than maybe 2 inches or less than 1 inch. And the machinery behind this is, again, the central limit theorem and our intervals. And the basic idea is that as I get a bigger and bigger sample, those samples are more likely to get close to the population average. So basically, if I want to find a sample size that gives me a certain margin of error, I just need if I need a certain margin of error and I don't have it yet, maybe I can get that margin of error by boosting my sample size. Now, in the mathematical sense, whenever we are doing this for averages, we're going to use the same formula that we used when dealing with the z-interval. And whenever we're dealing with proportions, we're going to use the same formula we used in proportion intervals. All right. Now, let me flip back to what those intervals were. So if you flip towards the z-interval, way back in 8.1, we saw that the z-interval was this. Again, my point estimate is the sample average, and then I build in some margin of error. So basically, if I want to figure out how much error I have, I'm looking at this part of the formula. Now, we don't do that with our t-intervals because if you recall, the t values depend on your sample size. So both the n and the t would be based on your sample size, so that's messy. So when we're dealing with averages, we're always going to use the z-interval and the z-interval margin of error, okay? That way, there's only one letter here that depends on my sample size, and that's n, all right? The other interval we used was the proportion interval. And the proportion interval, we see this as our margin of error, this piece right here. So we have our point estimate, which is our sample proportion, and we're adding and subtracting a little bit of error. This thing is the error, so that's what we'll be using. Now, what that looks like is this. I can forget about the actual point estimate when I'm talking about sample size, and I can just focus in on the amount of error that we've built in. So when we're dealing with means, you go back to that z-interval. The part of the z-interval that's the error is the z of alpha over 2 times sigma over square root of n. And for proportions, the error is the z value times square root of p hat q hat divided by square root of n. So let's start out with this one. Now, what I like to do is I like to write this equation every time. So how this is going to work in practicality is we're going to want a certain margin of error. So maybe, again, if we're dealing with heights, maybe I want that height error to be within 1 inch of what I'm looking for. In other words, I want the population average to be within 1 inch of my sample average. The z-value, that'll come from our confidence level. The standard deviation, that'll come from the problem itself. And so we're going to have this equation. It has 4 unknowns: error, z-value, standard deviation, and n. But what's going to happen is I'm going to be given 3 of them. I'm going to know my error that I want. I'm going to have a z-value that's coming from the confidence level. I'm going to be given a standard deviation. And then the n is the sample size. So all I have to do is put those 3 numbers in and then solve for n. So let's do this on an example. Let's say we want to find the height of all people from Mexico, the average height of people in Mexico. I want to make sure that I'm accurate within 0.5 inches or half an inch of the real average height. And I want to be 95% confident of my result. So I want to build this 95% confidence interval. And when it says you want to be accurate within a half an inch or 0.5 inches, that just means that the margin of error needs to be 0.5 or less. Now, this says we know the standard deviation is going to be 3 inches. Now, how do we know the standard deviation is going to be 3 inches? Maybe it came from a previous study. Maybe, who knows where it came from? Maybe we know that's the standard deviation for people in the US. But we'll assume that we know the standard deviation is 3 inches. Okay? Most of the times when you're doing this in real life, you would have a standard deviation to go off of because you'll have a similar study done. So you're replicating studies most of the time. So if I want my margin of error to be half an inch, I want to be 95% confident, and I want my standard deviation to be 3, how large should my sample be? So here's how we do it. We go grab this formula. Obviously, we're talking about the average height in Mexico. So since I'm talking about the average height in Mexico, we're going to use the formula for the z-interval. Okay? Now, this says that the error is equal to z of alpha over 2 times the standard deviation divided by the square root of n. So what I'm going to do is I'm going to basically plug in what I know. We want the error to be within 0.5, a half of an inch. It says that my standard deviation is 3 inches. Now here's the hardest part. What is this z of alpha over 2? Well, if you recall back from the previous part of the notes, the previous videos, we actually created a table with all of these z values. So if you recall, 95% confidence level meant that the chance that I get it wrong is 0.05 or 5%. I divide that in 2 because we have 2 tails on each side of the normal curve. So you'd get 0.025 for your alpha over 2. And then to find your z-value, you just do inverse normal of that 0.025. Or excuse me, yeah, 0.025. So you do inverse normal of 0.025. And then obviously on a standard normal curve, the mean is 0, standard deviation is 1. And the z-value came out to about 1.96. So again, you can go back and check how we created that table, how we came up with all the alphas and alphas over 2's. So this says I want to be 95% confident. I want to have a 95% confidence interval. So I go back to that table and I look it up, and it turns out the z-value for a 95% confidence interval was 1.96. All right, now all we have to do is solve this. Now, in order to solve this equation, we need to take that square root of n, and we need to get it out of the denominator. So what we're going to do is we're going to take this equation, and what I would do is I would take and multiply on both sides by the square root of n. So I multiply the right-hand side by the square root of n, and I multiply the left-hand side by the square root of n. Okay? Now, notice what that's going to do to the right-hand side. One square root of n, I'm dividing. The other square root of n, I'm multiplying. So they're going to cancel each other out on the right-hand side. And what you're going to be left with, well, you're going to be left with no denominator on the right-hand side, but you'll be left with a 0.5 times the square root of n on the left-hand side. So that's what's going to happen. All right. Now this is a pretty straightforward solving from here. So once you have this equation, all I have to do is now divide both sides by 0.5. If I divide the left-hand side by 0.5, that goes away. The right-hand side becomes 1.96 times 3 divided by 0.5. So we have the square root of n is equal to this. Now what I like to do is I like to, at this point, type that into on my calculator. 1.96 times 3 divided by 0.5. That gives me 11.76. So let me go through all the steps now. I won't every time write all the steps, but I have 11.76 is the square root of n. Notice that's not what the sample size is. The sample size, well, the square root of n is 11.76. So what we're going to do is square both sides. So I take both sides, and to undo a square root, I have to take things to the second power. Oops. There we go. So square that side, and we get n is equal to, I apologize, 138.2976. Now, this is the one exception to our rounding to 2 decimal place rule. Okay? 138.2976. If I said go out and sample 138.2976 people, you would think I was crazy. So what we're going to do is we're just going to round to the nearest whole number, and we're going to say we should sample, or you should sample, or just sample 139 people. Now notice what I did. I went up to the nearest whole number. So I rounded, I always go up because notice the context of the problem. It said I wanted to be within a half an inch. It turns out that 138 0.2976 gives you exactly half an inch. So if I go up to the nearest whole number, I get slightly under a half an inch. If I would have said sample 138 people, you would have gotten slightly more than a half of an inch worth of error. So I always want to go up to the nearest whole number when we're doing these problems. So hopefully that's not too messy. Hopefully you followed that. Again, every time I write the error is equal to this, and then plug in my stuff, multiply both sides by the square root of n, divide by the coefficient, and then square both sides. So that's how it's done. Again, those z of alpha over 2's, those come from that table that we filled out. And on your test, you'll have a small table version, and the actual percentages in the sample size problem will have been on that small table on the test. So if it asks you about a 95% confidence interval and you're doing within a sample size problem, that 95% will be on the table. So here's what I'd like you to do. I'd like you to try this one on your own. Go ahead, push pause on the video, and then read it and do it on your own. So I switched over to the Word document here so I can plug things in. All right, so let me go through this. Hopefully you read it. Hopefully you did the whole thing. He wants to be 90% confident. Now 90% confident, again, go back to that table. 90% confident meant that 10% chance I have it wrong, 5% chance I have it wrong on the left, and 5% on the right. So alpha over 2 is 0.05. And if I do inverse normal of 0.05, that came out to 1.64. So what that tells me is that 90% confidence levels means my z-value is 1.64. Okay. It says the standard deviation is $1,100. And it also says that we want to be accurate within $150. So that's my margin of error there. So this is the setup. The error is 150. The z-value, again, because of 90% confidence, the z of alpha over 2 is 1.64. And we're accurate within 150. So, or excuse me, our standard deviation is 1100, so it goes there. Okay, so we'd multiply both sides by the square root of n. What that's going to do is it's going to get rid of my square root on the right-hand side, and it'll leave me with 150 is equal to 1.64 times 1100. Okay. Divide both sides by 150. If I do that, my calculator is going to not give me a whole great number, but it gives me 12.026666 blah blah blah, right? So 12.02666. Now one thing about this repeats. I would not want to round this at this stage to 12.03. Okay, you want to round it only at the very, very end. All right, so you don't want to round this to 12 or 12.03 before you do your square. So when you type it in your calculator, once you've calculated this, hit enter, and then just square whatever number you get. You can just hit caret 2 on that 12.02666. And what I got is that my sample size to be precisely $150 worth of error would have had to have been 144.64. So that's what you would need to get precisely 150 worth of error. We want to be within 150, so we would sample 145. Well, in this case, we're talking about sports reporters. All right, hopefully that makes sense. So again, hopefully that makes sense. Hopefully you've done that and can move along. All right, let's say this. I want you to do one more example. In this example, we're going to do average IQ in Michigan. So push pause on the video, do the example, and then we'll move forward. All right, so we want to be, well, the first thing I usually look at is how much error do I want to have? How much is the standard deviation and what's my confidence level? Okay, now that's for when we're finding averages. Maybe I should start with that. We want to look, are we looking for averages or are we creating confidence intervals for proportions? So are we creating confidence intervals for averages or proportions? In this case, it's pretty clear that we're talking about the average IQ. So the average IQ means that I am going to let me put this in. I apologize for that. So we're talking about average IQ. Okay, so we want to put the error formula that you get from the z interval. We know the standard deviation of IQ scores is 15, so we'll put that in for the standard deviation. We want to be 98% accurate. Again, we flip back to that table. 98% accurate. Well, that's not on my table, but I can fill it out. 98% accurate means I have a 2% chance of getting it wrong. That means 1% chance on each side, 0.01. When I do inverse norm of 0.01, comma 0, comma 1, I get a 2.33 as my z-value. So my z-value should be 2.33. All right. And I want my error to be a maximum of 3 points. So there we are. So we solve this in exactly the same way. Multiply both sides by n. I'm sorry. Multiply both sides by the square root of n. Then divide by the coefficient of the square root on the left-hand side. So in this case, we'd be dividing by 3. Takes longer to type it than it does to actually do it in my calculator. Again, I'm writing all the steps, but in reality, I probably wouldn't write this every time I do this. So we do the calculation, 2.33 times 15 divided by 3 comes out to 11.65. We square that number. And we get 135.7225. We write that down, 135.7225. Okay? So if we wanted to find the average IQ score in Michigan, and we wanted to make sure that we're accurate within 3 points, we better sample 136 people from Michigan. And there you have it. So that's how we deal with averages and finding sample sizes for averages. Okay? Now, what's going to happen when we move to proportions? Well, with proportions, I said this is the error. We got a z of alpha over 2 multiplied times the square root of p hat q hat. Remember, that was the sample proportion and of success and sample proportion of failure divided by square root of n. So it's going to look very, very similar, except instead of having a standard deviation, we're going to have a p hat and a q hat. So let's say that a medical researcher wishes to determine the percentage of females who take vitamins. So this medical researcher wants to be 99% confident, and he wants the estimate to be within 2 percentage points of the actual proportion. In other words, they want the margin of error to be within 2 percentage points. As a proportion, 2 percentage points is 0.02. And it says in a recent study, which we know that happened, 25% took vitamins. How large should my sample be? So here's what we do. We go back and we say, well, obviously we're dealing with proportions. So I go and I get the formula for the error of the proportions. Sorry about this. So I got this error. Now, just like before, we're going to start filling things in. So we want to be within 2 percentage points of the actual proportion. Now, what I would suggest is instead of writing the number 2 there, is we write these things as proportions. That's going to be probably the cleanest way to do it. So when you write your error, you want to write 2 percentage points as 0.02. Now, 99% confident, again, we flip back to the table. 99% means a 1% chance of getting it wrong. So that's a 0.5% or proportion of 0.005 on each tail. So we do inverse norm of 0.005. And you would find that the z-value is 2.58. Okay, again, flip back to your table if you're looking for that. Now, the only thing that we don't have is the p hat and the q hat right now filled in. But what we can use is the recent results. So recently, 25% of the 180 females took vitamins. So that means that success rate was 0.25. And we can just use 0.25 as an approximate for what our sample proportion is going to be. Now 0.25 is the proportion of success, so 0.75 is going to be the proportion of failure. And now we solve this in the exact same way we dealt with the other one. So in the exact same way we dealt with the other one, we're going to multiply both sides by the square root of n. Now I'm going to skip a step here. If I multiply both sides by the square root of n, we get 0.02 times the square root of n on the left-hand side. On the right-hand side, all I'm going to do is I'm going to cancel out that denominator. So on the right-hand side, all I'm going to be left with is that square root. So square root of 0.25 times 0.75. As always, my next step is to divide by my coefficient. In this case, that coefficient is 0.02. And then I'm going to calculate some number. That number might come out pretty ugly, but that's okay. Mine comes out as 55.8586, again, blah, blah, blah. All right? So square root of n is equal to right about 55.8586, blah, blah, blah. In order to get rid of the square root, I'm going to square both sides. And again, I'm not actually rounding this until the very end. I'm saying this is what I get in my calculator, 85863857. I'm sorry, 3854. I get that all in my calculator. So I'm just squaring that whole thing that's in my calculator. And what we get is 3,120.1875. That's my n. N equals 3120.1875. There you go. So what does that mean? That means in order for me to get this, in order for me to find out the percentage of females who took vitamins and be within 2 percentage points of the actual proportion that I want, I'm going to have to sample 3,121 females. So there we are. Notice all the similarities. The similarities, we put in the error, we put in the z-value, we put in some sort of a previous, well, it was standard deviation when we were dealing with averages. Now it's the proportion of success, proportion of failure. So there we are. All of the solving works in exactly the same way it did with averages. And that's what happens. So here's what I'd like you to do. I'd like you to try example 5 on your own. So push pause on the video and try example 5 on your own. All right, hopefully you did that. So everything's so similar to my last example. I'm just going to copy and paste what we did on our last example and then just change the numbers, okay? So we want to find out the proportion of adults in the U.S. who are obese. We want to be accurate within 3 percentage points, and we want to be 90% confidence. So last year, the CDC determined that 36.5% of United States adults are obese. So how big of a sample should I be, again, if I want to be 90% confident and be accurate within 3 percentage points? So this is obviously talking about proportions. So we're going to use the error formula for the proportions. The error in this case, I want to be within 3 percentage points. So the error is going to be 0.03. That's one of the things you have to pay really close attention to. A lot of people will put the number 3 there and get that incorrect. Make sure you put 0.03 because we're dealing with proportions. Now 90% confident, flip back to our table, 1.64 is our z-value when we are 90% confident. 36.5% in a previous study. So that means that the previous study had a percentage of success that was 0.365. And also, just take the complement of that, the percentage of failure would have had to be 0.635, oddly enough. Okay? At this point, now that we've set this up, I'd multiply both sides by the square root of n. We're going to get 0.03 times the square root of n on the left-hand side. On the right-hand side, I'm going to get 1.64 times that square root of 0.365 multiplied times 0.635. Okay? Once we've done that, we divide by this coefficient on both sides. Divide the left-hand side by 0.03. It's going to cancel that out. Divide the right-hand side by 0.03. And, well, the equation looks like this. I'm just going to type that into my calculator. And what I got is about 26.318 blah, 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 blah. So the square root of n would be equal to 26.318 Again, I'm not rounding until the very end. I'm squaring that number, and it would say n is equal to 692.6467, etc., etc. Again, we're going to round up to the nearest whole number. We would say that we should sample 693 U.S. adults. There you go. So if we wanted to find a confidence interval that was within 3 percentage points, we would want to sample 693 adults in the United States, obviously. Now, one thing, that we can look at with proportions that we cannot do with averages is we can actually go back and we can base our sample size even when there's not a previous study to go off of. So let's do this one. Let's say we wanted to find the proportion of, survey people from Michigan. We're going to find the proportion or the percentage of adults whose favorite holiday is Halloween. We want to be 90% confident, and we want the estimate to be within 2 percentage points of the actual proportion. How large should my sample be if I don't have a previous study to go off of? Now, the difficulty here is that no previous study. Well, let's actually start plugging things in. All right, here we go. So we know we're dealing with proportions. Percentages, proportions, same difference. We know we're going to use this formula here. When we start to plug this in, it looks all right. The error, we want to be within 2 percentage points of the actual proportion. Error becomes 0.02. 90% confidence means that the z is still 1.64. The trouble is, when we get to the square root of p hat q hat, we don't have a previous study to plug in here. Like in the previous two problems, with the females taking vitamins, I could use a recent study showed that 25%. So I could use 25% for my p hat. Here, with the proportion of obese adults, we had a previous study of 36.5% that I could use for my p hat. So what happens if I don't have a previous study? Well, basically, short scenario, or the short way to say this is we use the worst scenario possible. And with proportions, we actually have a worst scenario possible. The worst scenario possible is the 50-50 case. In other words, it's where my probability of success and my probability of failure are both 50%. All right? If that happens, then we get some really, well, we get our highest sample size. Okay? And it should make sense that that's sort of the hardest decision to make. Think about if you were some politician and 50% of your constituents liked a policy and 50% didn't, how would you vote on it? It's an easy vote if it's like a 90-10 issue. So if 90% of your constituents liked the policy, go ahead and vote for that policy. It becomes a harder issue when we get down to the 50-50 case. All right. Now, solving this works exactly in the same way as we did before. So we're going to take, oh, I can't do that, 0.02 times the square root of n and set that equal to 1.64 times the square root of 0.5 times 0.5. And then I'm going to divide by 0.02. I'm going to do that on my own. So what we end up with is that the square root of n is right about 41. In fact, it lands on 41 exactly. So 1.64 times the square root of 0.5 times 0.5, and then divide by 0.02, lands on whole number. This is the first time that's happened, but that's fine. We'll square both sides, just like always. So square both sides, and I get 1681. So we should sample, or if I wanted to do this experiment, we should sample 1,681 adults. Now again, if you did this from the US, then we do US adults. If you did it just from Michigan, you can do just Michigan adults. Notice I didn't have to go up a number because it landed on 1681 perfectly. So I didn't need to go up to 1682 or anything further than that. So all of that is basically just to say that with proportions, there is a worst case scenario, and so I don't actually need a previous study to do this work. I can assume it's going to come out in the worst case scenario of 50-50, and then solve it just like I do the others. Now we hope it doesn't come out. We hope that we have a previous study to deal with, like example 4 and example 5, because if I have a previous study, I'm going to be able to sample a little bit less people. But it is doable without a previous study. We just, again, assume the worst case scenario of 50-50. Now, by the way, just as a side note, if you look at these formulas, with proportions, there is a worst case scenario of 50-50 because there's bounds on what these have to be. These proportions always have to be between 0 and 1. The probability of success has to be between 0 and 1, and the probability of failure has to be the complement of that. But I point this out because we do not have a worst case scenario when we're talking about averages. There's no bound on the on the standard deviation. So when we're talking about averages, we do have to deal with a previous study, okay? So we do have to deal and have a standard deviation from some previous study. All right, the last thing I'm going to mention in this chapter is I talked about earlier that we do confidence intervals for averages, and we do confidence intervals for proportions. We just saw how to do sample sizes for averages and sample sizes when dealing with proportions. It turns out you can also do confidence intervals for things like standard deviation and variation. Okay? It does use a very different type of distribution called a chi-square distribution, but it is very doable. Okay, and if you wanted to learn more about that, you can read up on the chi-square distribution and then look at how to do those types of calculations in the book. Okay, I'm not going to do that here. So that is it for chapter 8. Make sure that you know your material, that you're up on everything, that you can do the test, do the practice test before you go in and take those tests. As always, if you have any questions, please get a hold of me and let me know.